definitely miss you over there. Just like,
I'm okay. All right, let's get started. So today, everybody, we're here. We're all here. Today, all we're talking about is getting ready for the test. Right? Test is on Tuesday. For those of you that are in this section, I'm making a recording so that I can, for the online sections, they can have the same review for the test you guys do. Okay? So, for the test, there are going to be a number of multiple choice questions, right? And then there are going to be some problems. The questions and the problems are going to be very similar to what you've already seen, right? So review the quizzes you've done for the 3 chapters we've covered so far. Review the problems. We're going to review problems again today to make sure everybody knows how to work these problems, right? So review the quizzes, review the problems, and those are the important things to do to get ready for this test. Okay? Does that make sense? All right. So, quizzes. We're not going to go over in here. Why are we not going to go over in quizzes in here? It gives you the answer. That's right. Right? Quiz gives you the answer. We don't need to cover it here. So we're going to go over the problems. All right. So back to the first homework set. Right? The radius of the sun, 704,000 kilometers. Oh, by the way, did you guys enjoy mapping out the planets and how far apart they are to give you a better idea of the scale of the solar system? All right. Now, Jupiter is large enough that actually could have taken those calipers and dialed them down to the size of Jupiter, and you still could have seen something. You kind of held it up to light just right. But most of the other planets are so small, except for Saturn. Most of the other planets are so small that had I tried to show you the size of the Earth on that scale with those calipers, I wouldn't have been able to. They just are not fine enough. I just have to close them and say, imagine, right? All right, so radius of the sun, 704,000 kilometers. Radius of the Earth, 6,300 kilometers. So how do we show that the sun's radius is about 100 times the radius of the Earth?
divide.
We just divide, right? So it's just the 704, 613 kilometers divided by 6,349. And that's it. It's going to come out to around 110, 111, 112, somewhere in there. Right? Okay. Question 2 of the first set. Right? We're going to build a model of the solar system on the quad. Now, you guys have all practiced this at this point. Right? That's what we did in lab.
Yep.
That's what we did in lab. Right? So you go and practice this. So you know what we're talking about then is, so the quad is 250 meters long. Right? We know that the farthest planet out, the farthest named planet out, we're still looking for planet 9. Right? Mystery planet that's out there maybe. So 250 meters is equivalent to 30.05 AU. So 250, right? So 250 meters divided by 30.05 AU is our scaling factor. Right? That's our scaling factor. And we're going to just simply take that factor, 250 divided by 30, and multiply by the distance that Mars is away from the sun, 1.524 AU. And that's going to give us where Mars would be on the quad. Right? So, bring this up. Mars, 1.524 AU times, then we have 250 meters divided by 30.05 AU. All right? Wonder what that works out to. Pull out my calculator.
12.7
12.7?
ish.
12.7 meters. 12.7 meters. 12.7 meters out to Mars. Barely, probably doesn't get you across the street from the Union. You start on the, especially if you start at the steps of the Union, you're out in the middle of the street, and that's Mars. All right? And Neptune is all the way out where the flagpoles are.
And that's your answer.
Yeah, that's the answer. All right?
When answering it on the test or quiz, whatever, we have to put the unit measurement.
Yeah, you'll need to know the units. All right? Okay. Question 3. All right? This is simply another scale problem. I'm saying if the Milky Way were about the size of a nickel, or 2 centimeters, and the Milky Way in its diameter is 100,000 light years, right? How big would the local group be in centimeters? So again, our scale factor. Our scale factor for this one is that we have 2 centimeters, right? 2 centimeters per 100,000 light years, right? 2 centimeters per 100,000 light years. And we're asking, how big would the local group be? Well, how big is the local group? But what is it? 3 million light years? Right? So,
Can you give us that?
yeah, I will give you that. So it's 3 million light years, right? So this ends up being 60 centimeters, which is 0.6 meters. So I don't have a nickel because, well, I almost never have real money. Right? So if the Milky Way is 2 centimeters, that's about this much right here at the end, right? 2 centimeters. And then 0.6 is that long. All right, that's the local group. There's the Milky Way. Okay? All right, this is just, why are we doing these conversions into things like centimeters? Right, right? It's really hard to imagine a light year. It's really hard to imagine a light year, right? So we have to convert it into something that we can get our hands around and say, all right, now I kind of get the size, right? Now our solar system is smaller than little bitty specks on here, right? When we're talking about the scale of our local group, our solar system is just a little bitty, not even a little bitty speck, because it's so small relative to the Milky Way. All right, so the next set of homework, right? Earth turns 1 full rotation in approximately 24 hours. How many degrees per hour does the sky turn? Remember, 1 full rotation is 360 degrees. Let me rephrase this. You are on a Walking Dead binge on Netflix. And each episode on Netflix is 45 minutes long. How many episodes can you watch in 6 hours? Right? And you just do the math to figure out how many episodes you can watch in 6 hours. This is kind of the same thing. We have full rotation is 24 hours. We have 360 degrees in a full rotation. So how many degrees do we have per hour? 15, right? So we're just going to take 360 degrees divided by 24, and we get 15 degrees per hour. All right? Or if you can watch, you know, one episode per 3/4 hours, how many episodes, this turns the math around a little bit. If you can watch one episode for 3.75 hours, which is 45 minutes, right? 0.75 hours, how many episodes can you watch in a day? So 0.75 hours per episode, right? You take 24 hours divided by 0.75 to get the number of episodes you can watch in a day. Assuming you don't sleep, pause, or anything like that, right? Does that make sense? Who doesn't binge watch on occasion on Netflix? All right. This one's a little harder. The second one on homework chapter 1, right? Cleveland is a latitude of 33.7 degrees. So the noon sun, right? Noon sun goes up and down, and so we're asking what's the highest altitude above the horizon of the noon sun during the summer. Now, when does this happen? Right? It happens when the North Pole, right, is leaning towards the sun. That's 23.5 degrees. And the sun comes in directly from there, right? North Pole is leaning towards the sun, which means that the sun is where? If you're at the equator, you're actually at a latitude of 23.5 degrees. I mean, if you're at the equator, you're here. But if you're at the spot where the sun shines directly down on you, right, straight down, you're at 23.5 degrees. And the sun is straight up, or 90 degrees above the horizon, right? Horizon's here, the sun is straight up if you're standing at 23.5 degrees. If you're at 23.5 degrees, you're somewhere in the Caribbean, right? But we are at 33.7 degrees, right? We're at 33.7 degrees. So instead of the sun being straight up or 90 degrees above the horizon, we have to back it off 10.2 degrees, right, to over there. So the sun, instead of being straight up, is 10.2 degrees closer to the horizon. So it's 90 minus the 10.2, right, or 79.8 degrees above the horizon. Does that make sense? So when you have to solve this problem, the best way to think of it is let's go to the easy case, which is where it's coming straight down. And it's coming straight down on 23.5 degrees. All right? Because the Earth is tilted 23.5 degrees towards the sun in the middle of the summer. The light comes straight in at 23.5 degrees latitude. We're at 33.7, so you just take 23.5, rotate the 10.2 to get to where we are, and now you're above the horizon 79.8 degrees. What if we change this problem to the equinox? Right? We're talking about the summer solstice. Suppose we now change it to one of the equinoxes. Where are we relative to the sun for one of the equinoxes? All right? The summer is when we're pointed towards the sun, right? The winter, the middle of the winter, or the winter solstice, is when we're pointed 23.5 degrees away from the sun, right? So the equinoxes are when the sun actually shines straight down on the equator. Happens in the mid-between the solstice. There's a spring equinox and a fall equinox. Spring equinox defines the beginning of spring. Fall equinox defines the beginning of fall. Right? March and September. So the sun is directly over the equator at the equinox. Boom, straight up at the equator. And how many degrees further up are we? 33.7. Right? So at the equinox, we have to take 33.7 degrees out of the 90 degrees to say how far is the sun above the horizon. So the sun at the equinox is 56.3 degrees above the horizon, something like that, right? Then what happens to us in the winter? Right? In the winter,
Sun's just on the other side.
in the winter, the sun shines directly down on a point that is minus 23.5 degrees latitude, and we're all the way up here at 33.7, right? So we have to go where in the winter, if you're at minus 23, which is meaning 23.5 degrees below the equator, right? You have to go 23.5 degrees to get to the equator, and then you have to go 33.7 degrees to get to us, right? So you have to subtract out both 23.5 and then 33.7 to get, in the winter, how far is the sun above the horizon. Make sense? Where is it relevant to your life? If you ever decide to build a house, right? If you ever decide to build a house, you want to pick the angle at which the sun starts to come in your windows. So that in the summer, when it's hot, the eaves of your house keep the sun from coming in the windows. And in the winter, when it's cold, the sun's low enough to come in the windows. Right? So you want to set up the eaves of your house so that they block the sun in the summer, but don't block the sun in the winter. That way, the south, again, this would be on the south side of your house here, right? That way your house doesn't take as much to heat and cool. So other people actually think hard about how we build houses to take advantage of the sun, right?
Your house set up like that?
Oh no, I rent. No. Okay. Third question of the second homework set. The moon's orbital period is 27.2 degrees, right? 27.2 days. Its synodic period is 29.5 days. So what's the difference between these two periods?
About 2 days. About 2 days.
Well, yes. But one is, if you imagine the Earth, one is the number of days it takes for the moon to go around the Earth from the moon's perspective. Right? I start off here, I go all the way around, I'm back to here. That's its orbital period. The other is how many days it takes for it to go around the Earth from our perspective. And those are different because the Earth is spinning. Right? And the moon's trying to chase us down during our day. And so it takes 29.5 days. It takes 2 days longer from our perspective because the moon is trying to chase us down. Right? Because we're spinning away from where it is. So on this problem, all you have to do is multiply the number of the days in the orbital period times the number of orbital periods you're given, right? The number of days in the synodic period times the number of synodic periods you're given, you then need to just divide by 365. Divide one of those. First, you calculate those and see that they're about the same, right? Then you divide by 365 to get how many years that is. And how many years did you get?
18-ish.
18-ish, right? 18 years. So, as I said in class, right, the first people to figure this out were magicians, because they could then predict the eclipses for the next 18 years, right? Once they realized there was an 18-year pattern, all they had to do was write it down, and then you could pretend to be a genius and say there's going to be an eclipse tomorrow. Right?
You said that,
What's that?
one more time.
So you're going to divide, you're going to take this number and multiply it by that one, right? You're going to take this number, the 29, and multiply it by 223, and just verify that they are about the same, right? Now the question is, how many years is that? What you have is how many days it is. And there are 365 days in a year. So you divide that number you get by 365 to get how many years you have.
Oh, you're getting two numbers.
You get two numbers, but they should be about the same, and then you just divide one of them by 365. Okay? Is that clear? All right. Okay. So, the great galaxy Andromeda has an angular diameter of 5 degrees, right? And it's 2.2 million light years away. What is its linear diameter? All right? So, the equation we had to use was the linear diameter is 2 pi times the distance times the angular diameter divided by 360 degrees, right? So we have the distance is 2.2 million light years. The big thing you have to remember is we've written in the word million, so the number you have to use, right? Let's go over to Word. So 2.2 million, you have to remember you have to write it as 2,200,000, right? And so we're doing the length is 2 pi d times alpha over 360. Right? 2 times pi times the 2,200,000 times alpha, and alpha was just 5 degrees. Right? Alpha is just 5 degrees. So, once we're through going through all of this, if any of you are struggling with how to do this in your calculator, all right, stay after I let everybody else go, and we'll start working on calculators. Does that make sense? So, if you just haven't figured out yet how to do this in your calculator, let's go over it. What's that? That's where the D is. Okay, D. So I'll write it as D equals 2, right? Okay?
The answer's going to be in light years.
Light
yes.
years.
Okay.
It's going to be in light years. Second question. Suppose the planet is found with an orbital period of 88 years. How might you estimate its distance to the sun? Right? This is just Kepler's law. Right? What's Kepler's law?
P squared equals A cubed.
Right? P squared equals A cubed. P is the orbital period in years. Right? A is the distance from the sun in astronomical units. Right? Orbital period in years, distance from the sun in astronomical units. So this is asking for, this gives us 88 years and it's asking for the distance. So we need A, which is going to be P squared to the 1/3, right? If we have A and we're asking for P, P is A cubed to the 1/2. Right? And there are different ways to do this in your calculator. So if you don't know how to do this in your calculator, this is one of the things we can go over. Right?
And wouldn't it be, the square root of A cubed is the same as A cubed to
To
the
the 1/2. That's correct. That is correct. And some calculators have square root, some calculators have cube root.
Okay.
Right? You could even, well, I'm not going to.
Okay.
There are other ways to look. There are other ways to think about it, but this is the simplest. Right? So you just take 88, you square it, right? And then you raise it to the 1/3 power. The way you would type this in most calculators would be something like P squared, and you'd probably want parentheses, P squared to the 1/3, right? And this converted it over to how I wrote it, but see if I can, like that. P squared to the 1/3. Okay? Okay. So, sometime in the future, we spot a new planet at 22.9 AU around a star whose sun's mass is the same as our sun. Now, the important part there is because this other star has the same mass as our sun, Kepler's law still applies. Right? If it does not have the same mass as our sun, Kepler's law doesn't apply. Okay? So Kepler's law still applies. We're given how far out it is, and we're asked how long does it take. So we turn to this equation, E equals A cubed to the 1/2. And that tells us how many years it takes for that planet to go around its star. Okay? All of these make sense? Questions? Somebody has a question. Yes?
I still don't understand number 2 on the
Chapter
chapter 1.
1. Okay? Okay. This is the hardest problem. Let me see if I can find something that will help. Okay. Imagine this is the Earth, right? It's at a tilt of 23.5 degrees. In the summer, that means the sun is over here. And that means the sun, when it shines down directly on the Earth, shines down here, which is 23.5 degrees above the equator, right? And we are a little bit further along at 33.7. So if we were at 23.5 degrees, the sun would be straight overhead. But as you go up the Earth to 33.7, the sun drifts down 10.2 degrees. Right? So instead of being overhead, the sun is at 10.2 degrees. 33.7 minus 23.5. Right? So 33.7 minus 23.5, 10.2 degrees. Right? So we go up another 10.2 degrees to get to where Cleveland is. When we do that, the sun drifts 10.2 degrees down towards the horizon. That means the sun is 90 degrees minus 10.2 above the horizon. And that's the answer. Right? When it's winter, right? We're still at 33 degrees up here, but the sun's shining down here. And so we're much further away from the sun, and much more gets subtracted out, right? And then when we're at one of the equinoxes, we're either like this or like this, and the sun is shining straight in on the equator, right? Doesn't matter which one we're at, the sun's shining straight in on the equator, and then we're 33 degrees further up, 33.7 degrees further up. So at the equator, it's straight up. As you walk up from the equator to here, it goes down by 33.7 degrees. So 90 minus 33.7 tells us how far above the horizon is.
So you always subtract.
Yes, you always end up subtracting because we're asking how far above the horizon. That's typically what we measure, is how far above the horizon. We don't measure how far away from overhead. Right? Does that make that clear? Someone else has a question. I don't know who you are, and maybe you don't even know what the question is. Yep.
Multiple choice on the test in the chat.
It's going to be very similar to the quizzes. Right? It's very similar to the quizzes. Other questions? You guys are set. You're ready.
Good.
All right. So I'm going to let you go. Anybody that would like help with their calculator, please stay, and we will go over how to use the calculator. I probably will if we have enough.
Yeah, the crossback is very hard. We only had three baritone for
Do you have any documentation?
and then Myers tried out.
Do that, because that'll be a valid excuse for me.
You're not. Raquel. Theoretically, yes, but I guarantee times 5.
There's not really.
We've got fewer people require right now, and that's a good thing.
I think our product is very small. Hey, I was like, where y'all going to this year? Where y'all food from this year?
I don't know.
You don't know.
There is a plan for a very small, like, mini tour, but he hasn't told us any of the details yet. Technically, I'm on, like, the choir council, the choral librarian, which means I get to organize.